In this segment of the lecture, we're just going to briefly consider typing issues for the simply typed lambda calculus. Typing is not something that's a main topic of this course, so it's a really peripheral sort of consideration at this point, but to just include this here, it's to give you some idea of the approaches and issues that type systems sort of add to the picture for us. If you want to read more chapters in the Software Foundation book, there's many more about different type systems and typing for different sorts of constructs and so on and so forth. There's much more that could be said about this, and type systems are a very big area in programming language theory. So what's the idea of typing? Well, typing for programs is usually regarded as a way of detecting problems or potential problems in programs at the time that you analyze them, usually at compile time. Traditionally that is things like assigning some properties to values or to expressions and ensuring that the way those expressions or values are used is consistent with the type or the property of those things. So when we talk about the type, we mean things like, something or other is a number, or something is a function or a list, or that sort of thing in the standard programming sort of way. And we're interested in doing things like, if we've got a language like simply typed lambda calculus, we're interested in saying, well, we've got a term, what is the type of that term? Or maybe it doesn't have a type because it's an ill-typed thing that doesn't make any sense. And the second one of those is quite important, because usually when we go on try and do an evaluation of a term into a value, say, we don't want to try to evaluate things that are ill-typed, that don't really make sense. So we talked briefly before about examples such as doing an if expression where the condition is not a Boolean, or applying a function to an argument where the thing being applied is not actually a function. It's say a Boolean or a number or something. Okay, so type systems and typing relation that we'll look at here are all about trying to work out the types of terms, and if it's not possible to work out a type, then we sort of reject the program in some sense, and we only are interested in evaluation for correctly typed terms. And we'll see some of those properties in the next segment as well. So how do we go about thinking about typing for the simply typed lambda calculus? Well, if you think about a term like x applied to y, what's the type of that term? Well, as they say here, it depends on what the type of x is and what the type of y is. So we would want, for example, to know that, say, the variable x is bound to a function type, a value of some type that's a function, and y, we'd want y to have the same type as the argument of the function that x is bound to, and so on. And then if those conditions hold, then we would say that the type of the x applied to y is the return type of whatever x's function is. So this is the kind of reasoning that the type systems, typing relations, and so on will do. And we need to keep track along the way of the types of variables, because as we dive into terms to analyze their types, we need to keep track of the bindings of variables to particular types of values, and that's so we can use those types as we get deeper and deeper into terms. So this gamma thing here is a way of keeping track of that. So what we're going to define here is this relation written in this style, but it's just a three-part relation. So the first part is this gamma, so-called typing context. Explain what that is in a minute. The second part is a term that we're interested in typing, and the third part is the type that we determine is the type of that given the context gamma. And what the gamma gives us is a mapping from variables to their types. So it's basically a way of saying we've collected some information about variables that are in scope when we're considering a term, and we know what type each of those variables are. It's a little bit similar to saying when you're inside a method in Java and you see the name of a variable, you can get some information from, say, the argument list of the method to find out what the type of that variable is if it's an argument to the method, and so on. So gamma is where we keep track of that information. And it's a partial map to types from, remember that partial maps map IDs to options. So in this case, the output is an option type. In other words, it might be that we don't know anything about a particular variable if it's never been mentioned anywhere else. So we can say, well, we don't know what the type of that variable is, but if we do know, we'll get an option that's got the type in it. So we'll see how that's used as we go along. So in the usual style, we're going to just look at the inference rules in a sort of informal version first. So in each case, the bottom of the line will be a gamma, a term, and a type. And we're going to give one rule for each kind of term that we can have. So if the term is a variable, then what we need to do is we need to use gamma to look up the variable, and it needs to be there, and it needs to be some type t. Okay, so if the gamma doesn't know what x is, then this rule doesn't apply. If gamma knows what x is, then we'll get the type back, and then that's the type that the term x has in the context gamma. Okay, so it's just a lookup operation. Okay, so what about abstraction? So if we've got an abstraction like this, what's the type of an abstraction? Well, it's going to be a function type, and it's going to be a function from the type of the argument, which is t1, if I can get that highlighted nicely, t11, right? So it's going to be a function from t11s to somethings, but you'll notice that the program, the term here, doesn't mention anything about what the return type of this function is, right? Because in this kind of anonymous function notation, there's no requirement to say what the output type is of the function, just what the argument type is. So we need to look at the body, which in this case is this t12, and say, well, what's the type of that? Which is what this judgment on the top is doing. So t12 appears here, but we need to consider the type of t12 in a context that's what we have already extended with the notion that x is a t11, because that argument is in scope for the t12, the lowercase t12. Okay, because in general lowercase t12 will include some x's, so we need to know what the type of x is for that to be typed correctly. So if we can do that and we get some type t12 back as the type of the body under the assumption that x is a t11, then we get the output type is a t11 to a t12. Okay, what about application? So here's an application. We need two things here. We need that t1 is a function. So we have to be able to type t1 to be of some function type. And we'll just call the function type t11 arrow t12. And in this language, we need t2, which is the argument value. It has to have the same type as the argument type of the function. So that's t11 in this case. And as a result of applying t1 to t2, we get the output type of the function, which is t12. So what about Boolean constants? So they're easy. So true is a bool, false is a bool. That's easy. And if you have an if then else, well, first thing is we want T1 to be a bool, which is what this is saying. And T2 and T3, we don't care what they are, as long as they're the same. So they could be bool, they could be a function, whatever, it doesn't matter. And so if they are the same, then the type of the whole if is that type, whatever that happens to be. Okay, and so you can see hopefully from these rules that if these rules apply, they put quite a lot of constraints over what the legal programs are allowed to be. Like we can't write a program where the T1 here is a function, because there are no rules that cover typing for that case. The only one that applies is the one that says T1 has to be a bool. Similarly, in the application rule, if we wrote a program where T1 actually had the type bool, then this rule wouldn't apply, because this requires T1 to have a function type. And there are no other rules that apply for applications. So if T1 turns out to be a bool, then that program would be ill-typed. So we wouldn't have to deal with it later on. So that's really the main aim of these rules, is to systematically work out what the type of everything is and place some constraints on the legal programs that we're allowed to write. Okay, so that's the informal version. We can get a formal version in the sort of pretty much the usual style that we've been doing all the way along. So this is a three-place relation. So that's the context, that's the gamma, that's the term, which is the t and the little t, and that's the type, which is the big T. Okay, and just like there's 6 rules six inference rules, there are 6 constructors that correspond to those rules. So for example, the TAP one here, you can see that the assumptions are that T1 is an arrow type, T2 is the same type as the input type of the arrow, and the application is the same type as the output type of the arrow. So these correspond directly to what we've got above. You notice that there's a little bit of option stuff going on here, so that when we look up a variable in gamma, we get sum of t back, because the map stores options instead of just types. Otherwise, this is all pretty straightforward to what's above. Okay, and just a few examples. So we can have things like here we have an abstraction with a Boolean argument, and the body is just a use of that argument. We can use an empty context. In other words, we don't know the type of any variables, right, which is fine because there are no free variables in this term, so we don't need to know any other variables. And we can show that the type of this abstraction is bool, arrow, bool, just by applying the let's catch up. So if we apply the TABS rule from up here, which is the only one that applies to things that will be abstractions, or that are abstractions. So we get the sub-goal, which says that we have to work out that x is a bool under the assumption that we have an empty context updated with x being a bool. So that's going to be easy. We can use the tvar rule for that, which just turns into a simple use of the update, which solves easily. Okay, so that's usually it's pretty simple to apply these things. So you can have a look at the second example, which is a bit more complicated. And typing example 3, I think, is the final. Yeah, is the final homework exercise. So you have to work out what the type. Show that the type of. So this is stated in a sort of slightly more tricky way, which is this is your term, this big thing here. We've got an empty context to start with, and what you're trying to do is find a type T that correctly types this. So the theorem doesn't tell you what the type has to be. You have to work that out in the proof. Okay. Okay, so we'll stop there for typing. There's a few more examples you can have a look at, and we'll come back with a few properties to finish up.